Okay, so we would continue what we have been discussing uh, in the last class. Uh, so we were discussing parallel force systems. We're actually discussing force systems, and in uh, in that we looked into two different kind of systems. One was parallel force system, and the other one was planar force system. And we explored certain property of both of this, wherein they could both be reduced into a single force equivalent systems. Okay. Now we didn't look into general three-dimensional problems, so today we would do general 3D problems. Okay. So far in this chapter, which is essentially the chapter 2 of your textbook, um, we are learning about reducing a force system involving a number of forces and moments to their simplest forms. Okay, and that's what we have been trying. So in general, what we know is we can, if there is a rigid body on which multiple forces are acting, let's say F1, F2, F3, and also certain couple moments are acting. Okay, that can for sure be reduced into an equivalent system wherein there is just a single resultant force R and a single resultant moment. Now this R has this expression, quite obvious, and the moment has this expression, where Ri is the position vector of the ith force. So this is R1, this is R2, R3, and so on, and plus all the moments that are there. Okay, that we know we can easily do. Not easily, but simply. So that can be obtained for any general force system, general 3D force system. Now we saw that in some cases, okay, let's say in these two cases, it is evident that the resultant force and the resultant moment are going to be normal to one another. So in that case, the entire force system could be reduced into a single force system. So there is a third equivalent now, where instead of O, I can move the whole thing to another point. Let's call it P. So there I only need to show, I mean, if the resultant were to pass through that point, if the line of action of R is supposed to include P, then then we would not need any other couple moment. Okay, this entire AMR, as we discussed, is sum of multiple couple moments. So these are individual couple moments, and these are also certain couple moments. Now these couple moments came from the original system as it is, and this came here because forces from each location were shifted to O. So but if I shift all the forces to P, uh, and then the resultant is the same expression, and then I would not need any moment correction. The net moment correction, actually there is a moment correction, but yeah, this one we would call as, so there is a difference. This one is mr but with respect to o. So the net moment correction mrp is also there, which just happens to be zero. Okay, so the entire system can be represented with a single force passing through p. I mean, if fortunately we could have originally chosen p instead of o, and we reduce the entire system to an equivalent system here, we would be getting only the resultant force. The resultant moment becomes zero. Okay, the net moment required would be zero. Okay, now even if we are not fortunately able to identify p on the first go, we can do that with respect to any arbitrary point o, and then we can determine at which point must we shift the resultant so that we don't need any other moment. Okay, to get the net effect of the original force system. So that way we get the simplest equivalent force system. Okay, but that comes with a condition that this has to be true, then only such a system can be obtained. Okay, so now we would look into some general 3D problems. Okay, so let's look at problem number 1 in 48. So there are a couple of cables applying some tensile load on the rod. Okay, I just need you to notice one thing that I have been repeating over and over again. When we are talking about a force system, okay, that could be only a set of forces that are acting on a given rigid body. Okay, that need not be that can be only a subset of all the forces that are acting on that rigid body. Okay, so that is so we are only trying to get the equivalent of that subset. Of course, there will be certain forces coming from the origin O over there, or the support O over there, which may or may not result into the equilibrium of the rigid body. Okay, that means under the action of those cable tension, the mast may fall in one side. Okay, that is also a possibility. But the thing is, it's when we are trying to get the equivalent, it's not necessarily the complete picture. Okay, so let's say only these two forces I'm trying to get an equivalent of. Okay, uh, so for this problem, what you would first do, you try to get the position vectors of, let's say, D, C, A, and B, and then try to get the position vector of D with respect to C. So don't miss any step. Okay, first write down the position vector with respect to origin, okay, of each point. For example, B is going to be how much? 6j meter. Okay, so RB is 6j meter. Okay. So similarly, you can identify the position vector of D, that is going to be 2y minus 3j meter. Okay, and you can of course identify the position vector of C and A, where C is 6k meter and A is 8k meter, and from the position vectors of all of this, you can identify the position vectors, okay, of D with respect to C and B with respect to A, so that you can identify the unit vectors along the cables. And once you do so, you can have the Cartesian representation of the forces FD and FB. So, so let's try that. Okay. Okay. So from this figure, we can identify the position vector of RA, RB, RC, and RD. Okay. So you can write those down. Okay. And from that we can identify how much is B with respect to A, how much is it, and D with respect to C. What is the position vector of B with respect to A? Can you hear my voice?
Yes, sir.
Yes, sir. Yes, sir.
Okay. So have you calculated position vector of B with respect to A?
Yes, sir.
How much is it?
Sir, it's 6 j cap minus 8 k cap.
Okay. Meter, right? And
Yes, sir.
and the D with respect to C?
Sir, it's coming 2I minus 3j minus 6k.
Okay. So your job is to get then the position vector EAB. So how much is it going to be? And the position vector of CD?
Sir, it's 2 by 7 I minus 3 by 7 j minus 6 by 7 k.
Okay. If you recall, position vector, the unit vector along AB is RB with respect to A dividing with its own magnitude. Okay. So in this way, we can have the position vectors. And once we have the position vectors, we can find out, let's say, if B is the magnitude FB times EAB. Okay. And same thing applies to FD. So how much is FB then?
Excuse me, sir. Someone is trying to enter the class, sir.
I mean, I have accepted probably 60 people. Okay. I mean, 2 times over for at least 15 people I have accepted.
Actually, sir, this classes CRE haven't provided the link in the official group. That's why people are coming late.
Okay. So if you are looking for the link, so the thing is, I'm using the same link for past few classes. Okay, and it's going to remain the same. Anyways, so it's very easy to write down the expression for the force vector. So how much is the force Cartesian in our Cartesian components?
Sir, for FP it's 3I cap minus 4K cap, and FD is 2
Unit is
Newton.
mandatory,
Newton.
kilonewton, and
Okay.
FD
FD it's 2I cap minus 3J cap minus 6K cap.
Sir,
yes.
sir, FB should be 3j minus 4k.
Okay.
Yes, sir. 3J minus 4.
Okay.
Yes, yes.
Okay. So okay. So once we have the forces, we also know the position vector of each force. Now you might choose to take the position vector along the line OA, okay, of each force, or maybe for one of the, for if you can take the position vector RB, and because you already have, you know, the expression for all the four, RA, RC, everything. Or you can take for the FD, you can take the position vector of C with respect to O, or the position vector of D with respect to O, in case you are trying to get the equivalent force system about O. Okay, so that is the that is actually the problem statement. Try to get the equivalent force system about O. So for all the things that are happening in this diagram can be equivalently represented with this mask showing here. There would be some resultant force acting on it, and some resultant moment acting at O. Okay, just identify what are the resultant force and the moment if we are to represent the equivalent force system at O. R is simple because it is, you know, just the addition of vector addition of the forces. Sorry.
Sir, the R is coming 2y minus 10k,
Okay.
and the torque is minus 6i plus 12j.
Sorry, the reaction, the resultant, sorry, not reaction, resultant force is just 2y minus 10k.
Yes, sir. The J component is balanced.
J component is balanced. Okay. Okay, okay. So 4 plus 6 gives you 10, and 3 and 3 are cancelling out. Okay. And how much is the resultant moment? By the way, that is with respect to O. How much is the resultant moment? Please mention.
Sir, it's coming. Sir, it's coming minus 6i plus 12j.
Unit?
Sir, plus 12j.
Yes, 12J. What is the unit?
Sir, kilonewton meter.
Okay. So never miss to mention the unit, and never miss to represent for a moment the point about which are you trying to get the moment. Okay, so so do mention about which point are you getting the moment. Okay, now now can you tell me uh, if this force system can be reduced into a third equivalent, wherein you can simply represent that with a single force at a passing through a single location. Can you do that, and how do you answer that? How do you know whether or not you can represent the entire system as a single force equivalent? By checking the orthogonality, whether or not R and M are, these are normal to one another. And how do you do that? By taking a dot product. Okay, so check whether this dot product goes to 0. If it does, then they are normal to one another. Then they can be reduced into a simpler equivalent, or the simplest equivalent system. Is the dot product coming to be 0?
No, sir.
No, right? Because
No, sir. It's
two i's, but k and j doesn't produce anything, so it's obviously non-zero. So so the only way for now, the only way is to leave it like that. Okay, we'll move on to the next problem. Okay, so for this problem, I hope you can look at this. I mean, you can understand what's happening over here. So okay, for some reason in the diagram there are a couple of x-axis, but this one is supposed to be y. Okay, it's printed mistakenly. So this one is x and this one is y. Okay, so it's a right-handed system. Okay, just take it to be a right-handed system. So in this case also, your job is to get the equivalent force system at O. So this one is not numbered, okay, but let's say you can number on your own, or not labeled. I mean, by numbered I mean not labeled. So you can label different points. So of course the origin is O, but let's say the pipe extends from there. And then it bends. So so this one we would mark as A, where the bending starts. Then it bends by a certain angle and becomes parallel to y-axis. And then it bends by 90 degree to become parallel with z-axis. And that's where all the bending ends. Okay, so and the tip, and then there is a tip of the pipe. So so I'm just labeling them as A, B, and C. Okay, so so luckily for us, the forces at A and C, we have the Cartesian representation already given for them. Okay, so I hope you can see what are the numbers. Okay, so your job is to get the resultant force. So for this one, you are trying to give me this resultant force and this resultant moment. Okay, so try to uh, find out the expression for R and the resultant moment with respect to O.
Sir,
Yes,
the resultant force is minus 30 I cap plus 15 J cap plus 45 K cap LB pound, and the resultant
plus
moment
15
is
J cap
yes sir,
and then 45 K cap
plus 45 K cap.
LB, right?
Yes sir, pound.
A- and the
Mom-
resultant moment about O.
I am getting it 17.5 I cap
Mhm.
minus minus 150 J cap plus 135 K cap.
Unit.
Feet pound.
Mhm.
Oh sorry,
Pound
pound
feet.
feet. Pound feet.
Foot pound is the unit of energy.
Energies.
Okay, so this needs to be verified. I mean, the resultant force is quite obvious, but the moment needs to be verified. Can anyone else confirm that this is correct?
Sir, I am getting another result.
Okay, what is it?
Sir, it's coming 160I
Mhm.
minus 107.5 J
Okay,
and plus 122.5 K.
okay. Okay. So I need answer from somebody
Sir,
else.
I'm getting the same answer as the first one, just
Mm-hmm.
125k, not 135. Rest is
Okay.
same.
Okay. So this one you are getting 125. Okay. I hope you are using cross product, okay, and not trying to get the normal distance and all. Number one, and mm, I mean the proper cross product of the exact points. Okay, for example, how much is RA? RA, I believe, is 2I plus 1.5J in fit. Okay, and for F1, so this quantity is supposed to be RA cross F1 and RC cross F2, and RC, you see RC with respect to A is okay, I think I made a mistake over here. It is supposed to be 1.5 I, and over here it is supposed to be 2J. And RCA, it seems another 2J and another 2K. So I can find out that RC with respect to the origin is 1.5 I plus 4J plus 2K in fit. Okay. So these are the position vectors you are using, right?
Yes, it would be 125, sir. Yes, I am very with you.
Okay. Now my question is, the position vectors are correct, right? For all of you, you're getting the same
Yes,
set
sir.
of
Yes, sir.
position. Okay. So possibly this is the answer with 125 in it. Uh, so now the question is, uh, this be reduced into a single force system? So take a dot product and check whether the two quantities are orthogonal to one another. Are they coming out to be orthogonal?
না স্যার অর্থগোনাল আসছে না।
Okay, so obviously this cannot also be reduced into a single force system. Uh, okay, so now we will look at how we can address this. Okay, I was searching for an example where we would be able to reduce the system into a single force system. Okay, but so we'll now move on to the last variety of equivalent force system. But before going there, I would like to mention something. So in the classroom of yours, I have shared a link to a set of problem sheets. Okay, and that covers your entire syllabus. Okay, uh, because it appears to me you are not practicing enough problems. Okay, so whatever we would be covering so far, that means by today's class, which is up to the chapter 2 of your from the book of Miriam and Craig. Okay, so that is going to be your assignment. Okay, and we would probably have a portion of a certain class. So let's say this 1 hour from Wednesday's class, where we would be discussing about if you are stuck with any of the problems from the problem sheet up to equivalent force system. Okay, so that we would discuss on the first one, or maybe let's say we would discuss about problem solving, and then we would continue with whatever we will be discussing in the next week, which is basically equilibrium of rigid bodies. Possibly we will start with two-dimensional equilibrium problems. Okay, so that we would start on Monday, and we would also continue that on Wednesday. But on Wednesday, 1 hour, possibly in the second hour, okay, we would be using that for addressing any problem that you are stuck, or that you are confused with in those problem sheets up to equivalent force system. Okay, so the next thing that you are about to learn is wrench resultant. I'm not quite sure whether deleting it was the good idea, but let's say wrench resultant. And for this, we would take a simpler example. Okay, so look at look at the problem number 50. Okay, so only couple of forces there. Okay, so the dimensions are in inches. Okay, so can you try to get the equivalent force system about O? So first job is to get equivalent force system about O. See, the topic is range resultant, and we literally got a spanner in action, which is some form of range actually. So, so that we can, identify with the problem, with the naming of it. Okay, range resultant. Okay, so for this figure, get the expression for the resultant force, of course, in Cartesian components. Unit is going to be pound, and the resultant moment about O, and this time the unit is going to be uh, pound inch. Now it is quite simple in this case, because you see the forces are parallel to uh, the unit vectors, or the basis vectors, or the x and y and z direction. It could be quite obvious, but I would still suggest representing them as f1 and f2. Okay, and taking the position vectors as r1 and r2. Okay, so in the end, I believe you are going to get this. Okay. Did you get the resultant moment?
Sir, it should be minus 320k.
Okay. Why it should
Sorry,
be
sir.
minus 320?
Sorry, sir. It should be minus 320j.
Just minus 320j.
Minus
Yeah, another
56 I
minus
cap,
56
minus
I cap,
30
minus
Minus
320.
56 I
Yeah,
cap
let
minus
me tell you
320
why.
K.
Yeah, why am I saying this? Okay, you see, if you look at this 8-inch distance, okay, the first thing that comes to your mind is that it is going to be 320j. But don't use your intuitions. Use actual position vector. Okay, then you are actually not considering 1.4 inches. Okay, that is also going to give you some component along x-axis as well. So yeah, how much is the value that you said?
So minus
Minus
56 I minus
Minus
320 J cap.
369.
56 sir, 56 I cap
Okay, 56i, and then
minus 320 J cap.
Okay. Is it plus 56 or minus?
Sir, I am getting minus.
Minus.
No,
Minus
minus,
It's minus.
56
It's
IK
down
plus
here.
320
minus.
IK. Plus 320 IK.
Okay. 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 So obviously the two are not normal to one another. Okay. So the question that you can ask is then what is the simplest resultant? Okay. Now now you see this is true. And why is this true? Because this can be thought of two parts, right? One part which is, so basically if you draw this diagram, so there is your spanner. Okay, so at O you are showing that there is a resultant force R. Okay, this is going to look something like this. It's actually going to be, yeah, something like this. This is your resultant force, and then the resultant moment is minus I and minus J. So yeah, it is going to look something like this. Okay, now the reason you cannot get this single force resultant, I'm not talking about the simplest resultant, because that is situation dependent. In this case also we can reduce it to something else, and that's what is a range resultant, but we cannot represent that into a single force system. And the reason for that is the resultant moment is not normal to the resultant force, which basically means the resultant moment can be decomposed into parts M parallel and M perpendicular. Okay. Now, can you tell me how much is M perpendicular? You have actually calculated in that quantity. Okay. It's actually R dot MRO, but then you'll have to divide that with the magnitude of R to get a unit vector along R. So that is the component of the, so R divided by the magnitude of R, let's call it the unit vector along R. So M parallel, the parallel component of the moment, and the vector form of it is M parallel times the unit vector R. Can you get M parallel for me? How much is M parallel? Is it 320 by root 5?
Yes, sir. 143.10.
So 320 by root 5, right?
Sir, yes.
Okay. So can you, acha. So now my I would like to also find out the M perpendicular. How do I do that? If I can get M parallel using dot product, how do I get M perpendicular? If dot product gives me the parallel part of the moment, what gives me the perpendicular component?
So using magnitude of cross product we can do.
Magnitude of cross product is not going to give you in perpendicular.
So the magnitude of the perpendicular means the under root of perpendicular square plus under m parallel square would
Yeah,
give
yeah.
that.
You can go on for a lot of things,
And
and yes, the cross product thing would also lead you to somewhere. But try to look at
the
this in
magnitude
this
of
way.
cross product by the magnitude of that R.
Yeah, yeah. I understand. I understand. A lot of ideas are coming. A lot of complicated ideas are coming. But what about some of addition and subtraction? I mean, I can represent M parallel as M parallel magnitude times ER, right?
Sir, we can just find out the unit vector in direction of r, and we can find out the imparallel
Yeah.
vector and subtract
Yes,
it from m.
that's what I'm saying. That's what I'm saying. So the unit vector we already found out. We don't have to find it out again. We already found out because we did this to get the dot product with MRO. So if I multiply the M parallel value with ER, so I had the parallel component of the moment along with its Cartesian representation. So this one has the Cartesian representation. All I have to do is to get M perpendicular, a simple vector subtraction. Does this make sense?
Yes, sir.
So I'll explain why we need M parallel and M perpendicular. The idea is now I'm trying to get an equivalent system. Now I'm trying to get an equivalent system again where we would have our spanner. Okay, this is our spanner. So now we would identify, what we can do is, you see, there is no way we can get rid of M parallel. So M parallel is going to be there. Okay. So earlier what was happening with, let's say, parallel and planar force system, what we would be having is M parallel equals 0. That means the component of the moment which is parallel to the resultant force, component of the resultant moment which is parallel to the resultant force, that would be 0. Okay, they were only evidently in perpendicular. Okay, and then we could reposition R in order to have a single force resultant. Now we can reposition R wherein I'll have a resultant force and a resultant moment acting along the same line. And this diagram may look confusing to you, okay, because I'm drawing it outside of the geometry. How can a force and a moment act outside of a geometry? You see, it's only for representation, mathematical representation. If this bugs you, then in your mind, imagine there is a rigid connection, some sort of rigid connection to this very point with this body here. Okay. So it's actually acting on the body, but having been able to represent that using a single force and a moment acting on the single line, we are, some way simplifying it, and that simplifying is not representative of the actual situation. But when it comes to a rigid body, that basically gives you the equivalent situation, and that is purely of mathematical interest. So whatever we have been doing so far, that is purely based on mathematics, because in the end, whether we solve an equilibrium problem or a dynamics problem, I need to have equivalent force systems. Okay, So purely on the mathematical purpose to in order to solve those problems. So this part is also mm, a mathematical operation with this representation, and at times this might not make enough sense physically. Okay, but then again, as I mentioned, if it bugs you really, you can think of there is a rigid connection. Okay, there is some invisible rigid body protruded part coming out of the spanner. Okay, so that means you can think of that point also as a part of the body. Okay, uh, so uh, so what I'm trying to say here is I can now get rid of him in perpendicular. That means instead of showing the resultant force system acting at O, I can show it to be acting at some other location at P. Okay, where the position vector of P is RPO with respect to O. So I can shift this thing. Okay, because these two diagrams are equivalent, which is also equivalent to the original system. Now this is equivalent to original system, but because this system is also equivalent to the uh, equivalent force system about O, which is equivalent to the original system. So this basically means M is M parallel plus, you see M parallel is a couple moment. So this part is actually your M perpendicular. Okay, so this you can effectively represent, because since the M perpendicular is perpendicular to R, this is a possible representation, which is not true for the total moment, but for the perpendicular part of the moment, this is true. Okay, but I think some of you have already developed some confusion with whatever we did over here. If you have any question, just let me know. So have you all understood what I'm doing over here? So I should be in a position to represent RPO cross R equals M perpendicular. Okay. Now if I take RPO to be xi plus yj plus zk, can I solve for the three coordinates, all the three coordinates?
No, sir.
And why is that? Because this point
Because
P is arbitrary.
any point can be taken on the line
Yes.
of action.
So that is physically okay. So this P prime is also a possible solution. Okay. And if I'm talking mathematically or in terms of linear algebra, this is the situation. You see this representation over here can also be represented like this. M perpendicular x, M perpendicular y, M perpendicular z. Okay, but over here, this is xyz, xz minus y, yz x. Okay, So you have a skew-symmetric matrix to invert to get x, y, and z. And because the determinant of this skew-symmetric tensor is 0, or the rank of this skew-symmetric tensor is 2, so there are only two independent parameters. The third is dependent. Okay, so it's not a valid question to ask to find out the point, okay, where the resultant must be shifted in order to have the range resultant, where the applied force and the applied moment are along the same line. Okay, so the valid question would be to find out the point of intersection of the range resultant with xy plane, which basically means the equation of the plane, equation of xy plane is z equals 0, which basically means set this to 0 and give me the position vector of, or find out the point of intersection of the range resultant, which is, this resultant force and this in parallel together forms the range resultant. Okay, so the simplest resultant in the most generalized situation is a range resultant, for which you can ask what is the point of intersection with any given plane. Now consider in one of the previous cases, okay, for example, in parallel and planar force system, we saw that the resultant force is perpendicular to the resultant moment. Okay, now that is those are the situations where it is evidently true, trivially true, always true. But you can also have a generalized force system, okay, where you might get a situation where the resultant force and the resultant moment might be perpendicular. And in that situation, you can reduce the system to a single force system, which would basically mean this it's a range resultant with m parallel equals 0. So the simplest resultant or single force resultant is the range resultant with m parallel equal to 0. Okay, and there also you can only ask this question. You see, in that case, MRO would simply be M perpendicular. And there also you can only ask this question, that you can only ask for the point of intersection with the simplest resultant, okay, or single force resultant with the given plane. I mean, you can also choose a YZ plane or a ZX plane. That's not a problem. But it cannot be a plane parallel to the resultant itself. Okay, it cannot be a plane parallel to the resultant itself. It can be any other plane. Okay, I mean, now you can say that there are infinite number of such planes. So I mean, you can imagine, let's say this is the direction of the resultant, and you can imagine a cylinder about that axis by taking the resultant as the axis. Then any plane which is tangential to that cylinder is not a valid plane. Okay, but there are a lot of planes possible, and at least xy or yz or zx, at least one of the three planes, okay, would be not parallel to, I mean, all the three planes cannot be parallel to R. Okay, so the questions that you would be getting there, you would definitely be given only a single plane to find the intersection with. Okay, so okay, so with that, I hope you understand this. So can you tell me what is the point of intersection of the simplest resultant, in this case a range resultant? Had m parallel been to 0, then that would be the single force resultant. Okay, can you tell me where is the point of intersection on the xy plane? Or
So
where does,
minus 6.4i plus 1.4j.
so RP is coming to be 6.4i,
Minus 6.4
and then
plus 1.4j.
okay. Now really think about this. This 1.4j is actually coming from the diagram itself. Okay, the original problem itself. Okay, which is actually mhm, trying to tell you that the resultant force should be shifted along the line of the spanner, which is basically parallel to x-axis. Okay. I'm not sure whether it's the correct answer, but others can confirm. Can anyone else tell me what you are getting? Could anyone else solve this one?
This one is minus 6.4 I cap plus 1.4 j.
Okay, so I believe it's the correct answer.
Yes, sir. It is coming.
Okay, so the next thing that we would do, yeah, so you see the two problems that we did before coming to this one. So figure number 48, both the problems are generalized 3D force situation, and in both cases the simplest resultant that you can get is the range resultant. Okay, because you see the resultant force and the resultant moment are not perpendicular to one another, which is to say that M parallel is non-zero. Okay, so if M parallel is non-zero, it will simply, in a range resultant, it will simply tag along with the resultant force as a couple moment. Okay, and if we have a situation where M parallel, where the resultant force and resultant moment are orthogonal to one another. For example, a planar force system or a parallel force system, or any general situation where that is true, then we can think of that M parallel being equal to 0. Okay, in that case we will get a single force resultant, which is simply a range resultant with M parallel equal to 0, and the approach is the very same. Okay, so even for these two problems you can try to get the range resultant, and maybe you can ask where is the point of intersection with the xy plane or the yz plane or zx plane. So now we would move on to a next problem, last problem of the day, and with that we would conclude equivalent force system. Okay, and I'm repeating again that you should look at the problem set that I have shared, and from that look at all the problems in the equivalent force system up to equivalent force system. Okay, and if you have any queries, any confusion, we can revert back on that on Wednesday. Okay, that is to say that is only for you to check whether you have any problem with any of the problems in the problem set. That doesn't mean that those are the only problems you should practice for class test or semester, and that obviously doesn't mean that I'll be giving you semester question or class test question from those problems. That is absolutely untrue. Okay, I mean, if you get one problem from that problem sheet anywhere in the semester and a class test, okay, you have to be extremely lucky for that. But and that's why you are supposed to also practice a lot of problems from the textbooks. Okay, the problem sets are supposed to be representative problems. Okay, the spectrum of difficulty, spectrum of variety. Okay, that is what is supposed to be represented through the problem sheets. Okay, so if you have problem with one of them, we can clear that, and then you can attempt more problems like that. That's the idea. So bottom line is, and it has been, is for you to practice a lot and lot of problems. Okay, so try the next problem, which is figure 51. You see three forces here, okay, and their corresponding position vectors. Okay, so determine the point of intersection with the xy plane. Okay, so get the range resultant for this one. Okay, and find out the point of intersection with the xy plane. Same problem statement. Okay, so what is the resultant moment in this case? Could you get the resultant moment for this one?
Sir, the answer is coming 4.45 I cap plus 1.98 J cap.
The coordinate.
Yes, sir.
Okay. Okay. But others can confirm. In fact, you can actually use the point P to directly get the resultant force system. You can directly get the resultant force system about point P. But you do not know the coordinates of P, X and Y. So how do you get the position vectors of A, B and C? So what you do is you can let them be unknowns, okay, and later be solved when you get the expression for the resultant resultant moment, okay. The perpendicular part of it should be 0. So when you get the resultant moment and resultant force about point P, the perpendicular part of the resultant moment should be 0, and that way you know the coordinates of point P.
Sir, I did not get it. Can you please?
Yeah, instead of trying to get the resultant force system first at A, let's say, and then trying to find out P, where you would have the range resultant, you can instead try to get the equivalent force system about point P. Okay, but you do not know the position vector of P. You can let that be an unknown. Okay, and with respect to that unknown position vector of P, you can get the equivalent force system at P. Okay, so let's say the position vector of B should be 4. B should be minus xi plus 4 minus y j meter. Okay, so you can continue doing that, and in this way, for example, the position vector of A should be minus x minus i minus x minus xi minus yj meter. So in this way you can get the equivalent force system at P, and the point P must be such that the equivalent system has a resultant force and also a resultant moment, but the perpendicular part of the resultant moment must be removed. So M resultant about P, MRP, okay, should be parallel to the resultant force R. Okay, which means the components must be proportional. The x component of the resultant force and the resultant moment should be proportional. The y component should be proportional, and the z component should be proportional.
So that means we will such that we will understood the FB vector with respect to point P and find
Sorry?
the moment.
Sorry, can you repeat?
Sir, then we will find the moment of each vector about point P. And,
yes, that's the idea.
And after that, we will imagine that to have a perpendicular component, then moment and dot product of the net force vector will be equals to 0.
No, the dot product should not be 0. You see,
sir,
no, let me finish. Don't think of in terms of dot product and cross product. You see, the resultant force and the resultant moment must be along the same line, which basically means that the components of the resultant force and the resultant moment at P, okay, should be proportional, the Cartesian components. For example, you can write in the end, let's call the components of the resultant moment with respect to P, which is MRP. Let the components be mx, my, and mz. Then mx by rx should be my by ry should equal to mz by rz. So mx by rx equals my by ry equals mz by rz. Now that is basically two equations. Okay, there are two equation signs, basically means there are two equations. Those are the two equations which will lead to the solution of the two unknown coordinates of P, x and y. Do you get the idea?
Yes, sir, I got the idea, but still there is some confusion. So because we are finding the range resultant, and we are doing such that the we are doing with the perpendicular component of the net moment.
Okay, I'll just repeat what I'm saying. Okay, so with, let's say, parallel force system or a planar force system, okay, we know for sure that the whatever point we choose to get the resultant force system, the resultant force and the resultant moment should be orthogonal to one another, which is to say that the dot product should be 0, or the parallel component of the moment, that is the component of the moment which is parallel to the resultant force, should be 0. And then we know that we can represent the system with a single force, okay, because the M parallel is 0. Now range resultant is a superset of that single force resultant, which means the single force resultant has m parallel equals 0, but the range resultant doesn't have does have a non-zero range m parallel. Okay, so but when you actually find out the point on a given plane through which the range resultant passes, the range resultant only has a parallel component of the moment, no perpendicular component of the moment. Okay, so we actually get rid of the perpendicular component by shifting the force to a different location, because it's the perpendicular component that we can get rid of. Okay, it's that part of the moment which is perpendicular to the resultant force is what we can get rid of by shifting the resultant force to a different location. And so the range resultant will have the resultant force and the component of the moment which is parallel to the resultant force itself. Now if P is the point on the xy plane through which the range resultant passes, and if we get the equivalent force system at P, so we would be getting the range resultant, which means the resultant is comprising of a single force and a single moment which is parallel to the force. Okay, so basically there is no imperpendicular when I'm trying to get the equivalent force system at P. Okay, which basically means the components of the moment, the Cartesian components of the moment and the Cartesian components of the resultant force about point P, if I were to get the equivalent force system about point P, the component of the moment about P and the components of the resultant force should be proportional, which is mx over rx equals my over ry equals mz over rz. Does that make sense now?
Yes, sir. It's now clear to me.
Okay, so that is the way to solve. That is just the other way to solve it. Okay, because all of these are equivalent force system, whether you try to get it about A or B or P or C, or the way it is, all are equivalent systems. Okay, I would ideally love to cover by today's class something called the free body diagram, but there are a lot of diagrams and I don't think there is enough time to cover it today. Okay, that is kind of prelude to equilibrium problems, but I hope I believe that has to be covered in the first half an hour of the Monday's class. Okay, yeah, so let's meet on Monday.